Hey, welcome to Chapter 8. And in Chapter 8, the first thing that we unfortunately have to say is that things in Chapter 7, where we just talked about substitution reactions, are not that simple. And that's what it says on the first page of your Chapter 8 course notes. Things are less simple than we pretended they were in the substitution chapter. So things are more complex than just substitution. There's another type of reaction that can and does happen. So everybody take a minute, look at this reaction, and try and classify. Is it a substitution, elimination, addition? What is actually happening here? So pause the video, decide on that, come back. You did that. Good job. What happened to the organic molecule? We took away that X, and we didn't really substitute with anything. We eliminated the X. So this is an elimination reaction. So that other reaction type that we're going to talk about extensively in this chapter is called an elimination reaction. Elimination reaction. And what happened here? Well, let's look at the bonds that were broken and the bonds that were formed. We have X minus over here. X, again, is a letter that we commonly put in the place of a halogen. So this could be chlorine, bromine, iodine. So what happened? Well, we broke a carbon halogen bond. We formed a base hydrogen bond. So we formed, we're on the formed side, or we're on the broken side. We formed a base hydrogen bond. What else was broken? Well, over here we have C4. This is C4H1, 2, 3, 4, 5, 6, 7, 8, H8. And this starting material is C4H9X. So essentially, one other thing that was broken had to have been a carbon hydrogen bond, because we have one fewer of those. So we'll even write that in right there. We also broke a CH sigma bond. What bonds were formed? We formed the base hydrogen bond, and we also formed a CC pi bond. So we can write in sigmas for all of these. These were all sigma bonds. We also formed a CC pi bond. That's kind of the what of the elimination reaction. And at this point, you guys have some experience pushing arrows to indicate the flow of electrons. You should be able to do that. So take a minute, pause the video again, and push the arrows, and we'll call this a concerted reaction. It turns out that just like substitution chemistry, it can be concerted or stepwise, but we're going to say that this is a concerted one. So push all the arrows that would be necessary to transform from the starting material to the product. You paused it, you're doing that, you're back. Okay, well, we formed a base hydrogen bond. So that has to happen. That base has to give up its electrons to that hydrogen. This carbon hydrogen bond has to break. Where is that pi bond going to come from? It's going to come from those electrons. So we would show the electrons in that bond going to make that pi bond. And in that process, this carbon can't have 10 electrons around it. So the carbon halogen bond has to break. So these are the arrows that would indicate an elimination reaction, and these arrows specifically all at the same time would be an E2 reaction because it's bimolecular, just like SN2 meant substitution, nucleophilic, bimolecular. This is an elimination, and with it being the concerted version, it's a bimolecular elimination. And this type of reaction is actually often referred to as a beta elimination. So what does that mean? Well, often we use these Greek alphabet letters, alpha, beta, in the place of A, B, C, D, E, F, G, etc. And alpha means one carbon away from something, and beta means two carbons away from something. So A, first letter of the alphabet, 1, B, second letter of the alphabet, 2. So what does that mean? So essentially we're talking about, well, what is being eliminated from this molecule? The halogen is. And where is the hydrogen that is being removed to do that elimination? Well, it's not on the alpha carbon. And concerning this X, so one carbon away from something, this would be the alpha position. And one more carbon over, 2 carbons away, would be the beta position. So why is this called beta elimination? Well, we took a hydrogen from the beta position to form the new pi bond, and that is what allowed the halogen to leave. So it's called beta elimination. So we're going to practice some more of that alpha beta with a few more examples, and just give me 1 second to rearrange the board. So we have 3 functional groups. We already talked about this one. This is a halogen, alkyl halide, and 1 carbon away from that's the alpha position, 2 carbons away is the beta position. So if we're calling this just a carbonyl, so this is a carbonyl, what is alpha to that carbonyl? What is beta to that carbonyl? Here's an amide. What is alpha to that amide? What is beta to that amide? So pause the video, draw in the alpha beta just like we talked about, and then unpause it. Okay, you did that. So like I said, this is the carbonyl. This would be alpha to the carbonyl, both of them, right? Because they're both 1 carbon away. And this would be beta to that carbonyl. As far as an amide, this is the amide. This would be the alpha position to that amide. That's the beta position to that amide. So in this chapter specifically, we're going to be pretty much entirely talking about alkyl halide. So we're always going to be talking about the alpha or the beta position to that halide, to where that leaving group is. But in future reactions and future chapters, we're going to be looking at as far out as that beta position. So that's why those are up as well. And just to kind of finish up this page, this chapter is all about elimination reactions. And just in general, we already saw it, but we're just going to put it on paper. We are forming what from what? We are forming what was the product in our elimination reaction. The product was, yeah, you got it. We're forming an alkene from an alkyl halide. So that's what this chapter is going to be focused on. We're going to see in this chapter that stereochemistry is going to play a big role. So why did we have to spend all that time learning about chair structures and Newman projections? Well, they're going to actually be really important in this chapter as far as how can we predict the product. So that's not useless knowledge. That's going to be really useful in understanding the stereochemistry and of the products that we're going to be forming. So more on that later.